Hi everyone, welcome to lesson 8 of our beginner CFD series from the Ansys Fluent Academy playlist. In this tutorial, we will simulate supersonic flow over a wedge inside Ansys Workbench, covering geometry creation in SpaceClaim, meshing in Ansys Meshing, and setup, run, and post-processing in Fluent like other previous tutorial. The goal is to model a two-dimensional inviscid supersonic flow over a wedge with a half angle of 15 degrees, as you can see here in this picture. The free stream Mach number is 3, pressure is 1 atmosphere, and the temperature is 300 Kelvin. We will model only the fluid regions above the wedge, taking advantage of symmetry. This green area over the wedge. So our domain includes one symmetry boundary at the bottom, one wall representing the wedge surface, and the remaining edges as the pressure Farfield boundaries. So let's start with the workbench. I have a workbench open here. So like other previous tutorial, I will drag a fluid flow fluent inside the workbench and then save this project. So I will save the supersonic flow over a wedge for the title of this project. So we will save this project and I can also change the name here for this fluid flow, so I can call it a supersonic flow. I will start with the SpaceClaim, click on the geometry, change the type to 2D, and then double click to the geometry and wait for SpaceClaim to be opened. Okay, now we have a SpaceClaim open and we have this geometry picture here with the coordination of each point and the geometry. So the purpose is, and the goal is, to create this green domain. Actually, we only need to create this domain and skip this solid part. So we can start with creating with one rectangular. So I will select the rectangular here and then select the sketch plane here, select new sketch plane, and then select the XY plane. Then use the plan view here, and then we have a normal view to XY plane. So we can start with this rectangular. You see the dimension is 500 millimeter to 1259 millimeter height. So I can start with clicking on the origin point, type 500, then use the tab key, go to the next dimension and type 1259, press enter. So this is the rectangular. For the other part, I will use 3 lines to create this one. So the dimension for this one is, as you can see, 1000 from here. This dimension is 1000 millimeter, and the height is 1259 minus 268. So it means that this dimension is 991. So I can start to create the lines. First of all, I will select the line tool, then select this edge, then type 1000 and then press tab key and then press enter. For the next line, as you can see, it's 991, and then press tab key and press enter again. And then finally we can connect these 2 points to each other, and then press escape button on the keyboard to skip from the line actually. So we can go and measure this dimension, this angle here. So we can go to measure, use the measure tool. For example, I can select this edge, hold the control key and select the next edge, and then you can see this dimension, this angle is 75. So it means that this one is 15 degree. So that's okay. I can go to the sketch and then end the sketch. As you can see, this sketching plane will be changed to a surface after clicking on the end sketch. So now time is to define the boundary conditions, symmetry, wedge, and the far field. So I will go to the group. First select this edge, use Ctrl G on the keyboard, and then type symmetry, press enter. Then I will select this edge, use Ctrl G or press on the create name selection, and then type wedge for this edge, and then I will select this line, hold the Ctrl key and select the other lines for the far field, pressure far field. Then use the Ctrl G again and type the name as far field for this edge. So as you can see, everything is done in the SpaceClaim, and we have 3 boundary and 1 surface. So now we can go to the workbench. Before that, I can close the SpaceClaim even without save, because you can save from here. I will press on the save to save the project, so the geometry will be saved. Now I can double click on the mesh and wait for a few seconds to open the Ansys Meshing. Okay, so now we are in the Ansys Meshing software here, so we can start to create the mesh. So first of all, we need to have the rectangular shape, quadratic meshes for this geometry. So we can start with the mesh, right click on the mesh and insert face meshing. Then I will select both of these faces and then press apply. So you should select with holding the Ctrl key to edges. So that's enough. So we have a quad type mesh for these 2 faces. Then we need to have actually some sizing for the edges. So I will go to the mesh, insert sizing. First of all, I'm going to select actually element size for these edges. So I will select the same for all of this one. Actually, you need to select the edge here. Then you can select edge, holding the Ctrl key, select all of these edges. And also you can select separately like this. For example, you can select here, and then in the element size you can put 0.01. I will add another sizing for this wedge, the same. So because these are the same, so you can select in one sizing, but here I'm adding 3 for all of each of these boundaries. So I need one more for the sizing. I will select these 4 edges, Farfield edges, and then press apply, press 0.01. So 3 element size with this dimension, with this element sizing for these edges. So I will press on the generate mesh by clicking on the right click on mesh, and so this is our mesh for this geometry. So everything is done. We can just update the mesh into the workbench, press update, and so mesh will be successfully sent to the workbench. I can close this meshing and will save the project. Now I can open the Ansys Fluent launcher by double clicking on the setup. So we have a Fluent launcher, and then select double precision, number of processor you can specify for your case. I will select 4 and then press start. Okay, now we have our domain here in the Ansys Fluent. We can start with the general part. I will select for this supersonic flow density base actually. So I will press on the density base. I will keep STD and other parameters here. I can go and check the mesh size. It is the number of cell is 17,024, and also I can check and perform mesh check. The minimum volume I will check, so there's no error. I can continue for the other part of setup. So for more detail about the pressure base and density base, I will add some explanation in this video. So you can pause the video later on and check here. Okay, now we can go here to the model and define our models here. First I will go to the viscous model and change this turbulent to inviscid type of the viscous model. This means the solver will neglect the viscous term in governing equation. So I will press on the OK. Then I have to activate the energy equation and press on OK. So sorry. The energy equation now is on. So for this supersonic flow, we need to define some properties in the fluid. We will select, we'll use this default material air here. The only thing is I will change to ideal gas, the density. After all, I will check the CP. Specific heat. I can keep these two specific heat and molecular weight as a default, and then press on the create and change, and then close this air. So now I have to go to physics tab and use the operation condition here. I will change this operating pressure to 0 and then press on OK. Okay, after all, we can go to cell zoom condition. We don't need to do anything. I just open this solid, this fluid surface. You can also change this name. It's actually a fluid type, as you can see here, but the only thing is the name is called solid, but you can change this name. I will keep it as it is. You can see I have this default material air here, so I can close this window. You don't need to do anything here, but now time is actually going to the boundary condition. As you can see, we have one internal, we don't need to do anything here, and we have one symmetry as we define in the SpaceClaim. But when you go to the wall, you can see under the wall type boundary condition, we have two boundary condition, one wedge, which is wall, so we can keep it as it is, but we have also Farfield here, so you need to change this type from wall to pressure Farfield. So I will right click on the pressure Farfield here, and under the type you can see here you have the different type. You can change this wall to these types, but in this case I will select the pressure Farfield. After that, you need to specify the value for the pressure Farfield parameters. As we remove the operation pressure in the operation condition part, you need to specify your gauge pressure. So this is 1 atmosphere. You can write in the Pascal unit 101.325. So it's equal to 1 atmosphere, and the Mach number is 3. The flow is in the x direction, so you can keep this one as 1 as the default value. So it means that this Mach number is in the x direction. And then finally you should go to thermal tab and check. This is 300 Kelvin, as you can see here, 300 Kelvin. So that's correct, and then press and apply and close this boundary condition. So as you can see, the pressure Farfield is under the inlet boundary condition. It's so it's in this category, and we have this wedge. Actually, here you can open, but you don't need to do anything here in this surface. Now we need to we can do some changes and some checks to be ready for the solve this problem. Under the solution, double click on the method and check. You need to select this and check also, this flow solution method to second order upwind. So I can keep this default value here. Okay, so next step is going to the control. You need to select one current number, CFL. I will select 0.1. For this supersonic wedge case, the flow involves an oblique shock, which is a sharp discontinuity if you use a large current number. So just let me one post in our channel. If you use a large current number like 1 or higher at the start, the solver can overshoot or even diverge because information jumps too far across cells in one iteration. Pressure and density gradients near the shock become unstable, and the residual start actually oscillating instead of converging. So setting CFL 0 equal to 0.1 keeps each update very small and stable. Actually, it's a conservative choice, slower, but it helps the solver capture the shock smoothly and ensure convergence in early iteration. So you can read this post in our channel to have a very short look on the CFL. So I will set this current number to 0.1. Then I will go to the monitor next to set the residuals. You can I will select 1E minus 6 or maybe 8. For all the equation, then press on OK. Then you can go to initialization, and instead of hybrid, this time I will select the standard. But before that, let me go back again to residual. For now, I will change it to E minus 6 for all the equations here, and again go to initialization. I will select a standard initialization. In the compute from, I will select Farfield, so you will see this value will be filled with the Farfield data, Farfield boundary condition data, like this pressure, x velocity based on the Mach number, and temperature. So I will press on the initialize. OK, and so it has been done. Actually, you will see we are using a relatively dense mesh for this actually setup. You can use some coarser mesh, for example, in the element size in the meshing part. You can select element size as 0.04, for example. Then after that, if you select that one, you have a better convergence. I mean, you will reach to the convergence very soon. But then you need to adapt mesh. For the you will have a shock here, so you need to modify your mesh here with the adapting mesh. So this is that's another way. So you can select first you can select either a very fine mesh like this one, or a coarse mesh, and then adapt the mesh in some area. I mean, in the shock region, you can actually decrease the size of the mesh and have a better mesh in that area, so you can see the differentiate between two sides of the shock wave actually. But in this case, I'm using this type of mesh. Now I can go to run calculation. Then for number of iteration, I will select 2000 and then press on calculate. Okay, so the solution has been started to reach the convergence. It takes a little bit time, so I will skip the video to reach the convergence, and then we will start the post-processing inside the Ansys Fluent. So as you can see with this coarse mesh, and after 2000 iteration, we didn't reach to our defined convergence. I mean 1e-6 for the residual. So I need more, maybe very more iterations to reach that number. So I will pause the video, and after convergence, I will start to explain and go start the post-processing. Okay, so after 8676 solution has been converged, as you can see here, and we have this pattern for our residual plots. So now we can start the post-processing and see some contours and vectors for this supersonic flow over a wedge. So we will go to the outline view, and then in the graphic we can start, for example, with the vector. So double click on the vectors to open the vector window. So here you can select the velocity magnitude and then press on the save and display, and you will see the velocity vector here, and this is the magnitude of the velocity. As you can see, there is a jump between these two areas. It means that we have a shock here over the edge, as you can see. So the so you can see this velocity vector here. You can also use the contours. For example, in the velocity, you can select the Mach number and then see the contour of Mach number here. As you can see here, the Mach number is 3, this red area, and then we have a shock here over the wedge here, and here we have the Mach number near 2.80 Mach number. You can also right click on each area to see the value. You have an approximation for the number. It's near 2.24 and 2.25 here, and here it's almost 3, as you can see. So this is the gradient for the Mach number, as you can see here. If you want better resolution here, you can adapt the mesh here. So maybe in another video I will explain how to adapt the mesh. I have a video for adapting mesh in the 3D geometry. You can also see in the channel for that one. So as you can see, this is the contour for the Mach number. So I will call it as Mach number and save it again. Then I will create a new contour, pressure, save and display. You will see the same pattern, the shock here over the wedge, and the pressure difference here between the two sides of the shock here. Just let me open it again and change the name to pressure. Save display again and close this window. Now let me display again the Mach number contours. Now we can create a actually plot for between two sides of this shock here. So if I create one line from here to here, so we can plot the Mach number, and you can see the jump between two sides of the shock. So to create a line, I will go to the results, and under the create a line, I will select line and rake. So I need 2 points from here to here. I will call it as Mach line, for example. So the first point is here, x is 0, and this point is 1.5 meter. We can check also, sorry, I can close this one. We can check here. So this is 1.5 meter, and the y for both this point and this point will be 0.268 meter. 0.268 meter. So I will copy and paste here and then create a line. So if I go to the XY plot here, double click, you will see I have a Mach line here, and I will call this one as Mach plot for the name of this plot. The position should be on the x-axis. Before that, let me show you this Mach line. Actually, first I will deselect this one, display this geometry, select the Mach line. As you can see, we have a straight line here. I can close here. So we have a XY plot on the x-axis in x direction. It's x direction on this plot. So I will go to the velocity, select the Mach number, and then select Mach line and save and display. As you can see here, the Mach number is 3 in upper side of the shock actually, and then we have a drop in the Mach number. It reaches almost roughly to 2.2. as you can see here. You can change the curve, for example, the pattern to this dash line, and apply and save, and you will see this jump between two sides of the actually shock. Okay, that's it for lesson 8 of our beginner CFD series from the Ansys Fluent Academy playlist. We simulate supersonic flow over a wedge and learn how to set up the geometry, mesh, and flow conditions in Ansys Workbench. So before closing this video, let me save the project in the Ansys Workbench. As you can see, all of this task has been done and ticked. So if you found this tutorial helpful, please don't forget to like, subscribe, and check out the next lessons in this series. Thanks for watching, and see you in the next video.